Hello again. In this lecture, we're going to learn about dividing radicals. And just to remind ourselves of a couple of formulas that are already or should be known, when we have the square root of anything squared, we are left with that anything. And for multiplying radicals, if underneath the radical we have a times b, we can break that up to the square root of a times the square root of b. Division has a similar rule to multiplication of radicals. If we have the square root of a divided by b, where that's the radicand, we can break it up to the square root of a divided by the square root of b. The key to using the multiplication rule and the division rule is that we're always searching for that perfect square from the very first rule that we've been given. So to start us off, let's start off with a nice problem that asks us to simplify. And we have the square root of 75 divided by the square root of 3. There's a couple different ways you can try tackling this. Like, you can simplify the square root of 75 and see if anything could cancel out. But truthfully and honestly, the easiest way to tackle this is notice 75 is not a perfect square, and neither is 3. But maybe, and just maybe, we hope that if we put them under one radical, and we reduce the radicand, like 75 divided by 3 is 25, that now we end up with a perfect square. And 25 is a perfect square. The square root of 25 is just 5. So this process from what our original problem was to putting it under one radical was in the hopes that we end up with the perfect square for the radicand. And that's what's going to motivate us. So let's tackle another problem a little bit different, where we have the square root of, and I misplaced my problem, give me 2 seconds, 2 over 72. Currently they're together. I don't want to just use the rule to break them apart and saying like, oh, that's going to be great. It's really depending on the problem. When I look at the radicand, currently there's not a perfect square jumping out at me, at least not yet. So my goal is to try to simplify the radicand to see if maybe a perfect square will come out. And sure enough, I can reduce the top part of the fraction by 2. 2 goes into itself once, and 2 goes into 72 36 times. Now I see a perfect square. In fact, 1's a perfect square as well. So this motivates me to break apart the radical into 2 pieces. And maybe my vocab isn't the best. I say break apart because you're going to view it as the square root of the numerator over the square root of the denominator, because it's all under one radical. So using the rule. And the square root of 1 is just 1. The square root of 36 is 6. No radicals in sight, and now we're happy. So these are both pretty nice problems. Let's see one that's a little bit different. That's not so nice per se. We have the square root of 16 over 5. Now, I see a perfect square because I have them memorized, and you'll slowly get yours memorized, and before you know it, you'll be shopping and you'll be thinking, oh, that's a nice number because it's a perfect square. Maybe. So, when we're looking at this, since I see that perfect square, my motivation is to go ahead and break it apart right away into 2 square roots. And the square root of 16 is 4. Now, looking at the denominator, we have the square root of 5, which cannot be reduced any further, so we'll leave it alone. But this poses a problem. We don't like seeing irrational numbers in the denominator. And the square root of 5 is what we call irrational. So, what we are going to do is rationalize the denominator. And how we're going to do that is pick something, anything really, specifically something that works for our interests, to make the square root go away. And the rule that we're living by, always we come back to, besides the multiplication and division rules, is the square root of something squared is just that something. Now, I can't just go squaring things. That's not acceptable. But let me write this rule a little bit differently. The square root of a squared is the same thing as the square root of a times a, which, using our multiplication rule, we could see the square root of a times the square root of a. And we already know from earlier that this result, no matter what, should give us the radicand a. So, this part here is key. When we think about something times the square root of 5 that will just get us something without a radical, well, here's our answer sitting in front of us right here. I'm going to take, let me extend my page real quick. We have 4 over the square root of 5 currently, and I'm going to multiply by 1. But I pick the 1, and the 1 I'm going to pick is the square root 5 divided by the square root 5. Same thing over same thing is 1. 1 times anything's the same. So I'm not changing anything, but when I multiply the bottom, square root 5 times square root 5 is now just 5. Why, you may ask? Well, look at the thing above. We have the square root of a times the square root a gets us just the radicand, a. That's what we had here. Or you could be long-winded and say, well, 5 times 5 is 25. The square root of 25 is 5. However you want to think of it. Now up top, we have a constant, he's rational, times this irrational square root 5. Rational people don't get along with irrational people, so they're stuck separate, and it's just 4 times square root 5. You can't mix them. We don't have a rule that says we can. And now this is our final answer. So this is what we call rationalizing the denominator. And I'll leave you on that note.